Once upon a time in a secluded cave, there lived a group of people. These are the Chained. They had spent their entire lives as prisoners in this cave, with their view limited to a barren wall. And this was only lit by the flickering shadows that cast upon it. These shadows are the creation of the Shadowcasters, who lived just above them. They manipulated objects behind the fire to cast these silhouettes. For the Chained, these shadows were their reality. They told stories about them and even named each shadows, believing these to be the true forms of their world. But then something extraordinary happened. One of the Chained was freed. He turned towards the fire and was immediately blinded by the light. At that point, he was unable to grasp the idea that the shadows were mere illusions. But his journey didn't end there. The freed also ventured outside the cave and began so overwhelmed by the complexity of this new reality. But gradually, from shadows to fire and then to real objects, his vision cleared. Finally, it was time for him to return to the cave. He was so excited to tell the rest of his fellow companions about his newfound revelations. However, there's only one problem. The freed, whose eyes had become so accustomed to the bright world above, would be blind when re-entering the cave. He later found himself unable to see the old shadows. The rest of the Chained people viewed his blindness as harmful, and they rejected his tales of the above world. To them, the familiar shadows remained their only truth, and they believed one should not attempt to deviate from their normal conformity. This story we just shared is the famous cave allegory from Plato. It reveals a deep aspect of human nature and perception. The story tells us that often our fear of the unknown and the challenge of reshaping our understanding of reality can overshadow our quest for truth. And so now let's delve deeper into this idea. Imagine a path of existence that stretches from the three-dimensional world of Alpha to the realm of Omega, as we labeled in our previous video here. We're going to show you how it's possible to access these distinct levels of consciousness using tangible technology that's achievable in our time. So bear with us for the next half an hour or so, as we dissect the specifics of how we reinterpret our existence. Before we dive into the steps to transcendence, let's establish some groundwork. The path from our starting point of existence to the ultimate state of knowledge isn't a journey everyone takes. Like the freed in our story, stepping into a new realm of understanding can be overwhelming and disorienting. It involves not just seeing new things, but also interpreting the world in a way that is fundamentally different from what was previously known. And many find comfort in familiar realities. The allure of the familiar, even when it's an illusion, often holds people back. As we ascend through these different levels, an intriguing pattern becomes evident. At each higher level, only a handful of entities are present. This is simply because by nature, it requires profound levels of perception and knowledge. And so, it's not about fewer numbers reaching these heights, it's about the increasing complexity of understanding that is required at each stage.
The goal of physics, we believe, is to find an equation which will allow us to unify all the forces of nature and allow us to read the mind of God. And so the final resolution could be that God is a mathematician.
If we transgress the boundaries of this concept, we may eventually find ourselves in a hypothetical tier of consciousness inhabited by only a select few. And ultimately, at the apex of this hierarchy, we'd find a singular entity. This solitary state reflects a consciousness so advanced that it stands unparalleled. A realm beyond our comprehension, devoid of ordinary thoughts, ideas, or other beings. This ultimate level might even surpass our previously mentioned Omega level, because in the concluding part of our last video, we pondered an existential question: who put all these boxes? This leads us to consider the possibility of even higher levels overseeing all possible worlds. So as we ventured through the realms of consciousness, we now face an intriguing question. How do we start our own journey of transcendence with the technology we have today? So in the next chapter of this video, we'll focus on tangible steps to transcend our current understanding using modern quantum technology. It's about transforming these abstract concepts to explore the possibilities of higher levels of consciousness. Transitioning from alpha's linear time perception to beta's nonlinear time perception involves a substantial shift in understanding. Just like someone from our community asked, wouldn't you need to live through the alpha linear timeline to have the experience needed to rewind and fast forward in time? That's exactly the kind of thought experiment we're going to explore today. And so, let's consider a specific workflow to illustrate this leap. We have our 35-year-old subject named Dr. Allen. She's a dedicated neuroscientist and has been involved in cognitive research for years. Her primary motivation for this experiment is to map specific memories with high fidelity from the last 3 years. To achieve this, we will utilize a brain-computer interface system, or BCI. The subject undergoes a prep session. An initial electroencephalogram, or EEG, and fMRI scan are conducted to map the normal brain activity patterns. This focuses on the prefrontal cortex and hippocampus, parts of the brain that play key roles in memory and decision-making. This device comprises a non-invasive headset with magnetic coils and electrodes. It's used to deliver targeted TMS, or transcranial magnetic stimulation. It begins at a low intensity of around 1 to 2 millitesla and gradually increases to a maximum of 5 millitesla. Then, a frequency range between 1 to 20 Hz stimulates memory recall. The subject concentrates on a specific period from her past research events that she wants to revisit. The EEG monitors her brain activity in real time, and fMRI data shows which regions of the brain are most active in this processing. This stage generates a comprehensive dataset outlining how the subject's brain recalls different types of memories. The validated dataset is used to train a machine learning model, specifically a neural network. This model is trained to recognize specific neural activation patterns and associate them with different memory types. For example, it recognizes key checkpoints within the 3-year timeline, such as experimental procedures, theoretical work, or collaborations with peers. By the end of this, we have a predictive model that is capable of identifying the recalled memory based on EEG and fMRI data. In structured memory recall sessions, the subject focuses on remembering specific days from the past 3 years of her research. Each recalled memory, along with its corresponding neural activity, is logged to create a robust and searchable database within the BCI device. We now have a detailed and personalized digital archive of the subject's past experiences. Whenever she wishes to revisit a particular moment, the system analyzes her current neural patterns, identifies the corresponding memory in the database, and finally retrieves it for review via a VR headset. This allows her to rewind to specific memories from her timeline, just like the nonlinear time perception of the beta level. But if you think this sounds too far-fetched, well, there's already a similar technology that is currently being deployed. This is the current capability of contemporary AI systems, which can interpret human thoughts by analyzing data from fMRI.
Here, they took human beings, they stuck them into an fMRI machine, and they showed them images. And they taught the AI, I want you to translate from the readings of the fMRI, so how blood is moving around in your brain, to the image. Can we reconstruct the image then? The AI then only looks at the brain, does not get to see the original image, and it's asked to reconstruct what it sees.
If you believe that reaching the beta level of perception is still feasible, then let's consider going even further. How can we ascend to the gamma level, where our test subject would be able to comprehend an entire database in one comprehensive view? If you remember from our previous explanation, this realm is about the ability to visualize every conceivable moment and every memory expansively. And so, the challenge becomes to envision an entire timeline as one unified database. So how could we make this possible? Transitioning to this level of perception isn't just about enhancing memory recall. It involves overcoming our physical limitations as humans. We need to think about enhancing brain neuron efficiency and increasing brain volume. Let's simplify to understand this better. Imagine each day's memories as a single data point or series of images. So that's roughly 1,095 data points for 3 years. Suppose viewing a one data point activates about 0.1% of the brain's neurons. With an estimated 90 billion neurons in the brain, that's around 90 million neurons for one memory sequence. But remember, this is a simplification. Keep in mind that neuronal activation for a memory isn't just about the number of neurons, but also their connections and the patterns they form. With that, if one day's memory requires activating 0.1% of the brain's neurons, theoretically, it could only process 1,000 days of memories at once. And in our case, this is not enough for a complete 3-year span. Now, this is why we need to upgrade our subject. If we enhance the synaptic transmission by, let's say, 15% more efficient, each neuron could fire and recover more rapidly. This would expand the total capacity from 1,000 days to about 1,150 days, according to our simplified model. And so in this scenario, we have set up an experiment where our subject experiences a full 3-year timeline all at once, but with the caveat of making improvements to her brain performance for complete gamma-level perception. In fact, this pattern should be consistent throughout our discussion today, that the higher the level of consciousness our subject ascends into, the more stringent the requirements for experiencing that simulated reality. And this ties back to our earlier discussion about the hypothetical tiers of consciousness and their occupation of higher reality realms.
And the mathematics itself suggests a movement in which any particular element of space may have a field which unfolds into the whole. I think there's an intelligence that's implicit there. So the consciousness is really our most immediate experience of this implicate order.
Let's recap where we are. In the gamma realm, we've glimpsed our timeline and past choices. Already, we've placed certain constraints on the physical characteristics, so not everyone can access this level. But for those who can, what if you aspire to reach even higher, not just observing, but also shaping this complex web of possibilities? So for this, we need to introduce a new system, something called the Quantum Decision Mapping Interface, or QDMI. As we leap into this new level, the complexity of our model increases exponentially. Each decision, each crossroad we encounter opens up a vast network of possible outcomes. Let's consider the following experiment. Our subject, Dr. Allen, wants to explore how different choices lead to various outcomes. Her main motive remains that she becomes the most successful researcher in her world. So it's safe to say that we're simulating this way beyond the 3-year timeframe. In this model, there will be realistic challenges that our subject might face, from securing funding to achieving breakthroughs with her team. And this is why we need the QDMI to help us create a visual representation of the decision trees. It works like this. As our subject progresses, the QDMI updates in real time, integrating new information and outcomes. So each node branches out into various paths representing different choices and will dynamically alter the decision tree structure. Additionally, the QDMI is also equipped with a feature called scenario reiteration, which allows our subject to hypothetically rewind to previous decision nodes and explores alternative paths. For instance, by mapping out different ways a grant proposal could play out, we create a complete hierarchy for that variable. If we can repeat this for other variables like academic networking and lab management, we will see how each choice impacts her career progression. If we could meticulously map out every conceivable probability and its corresponding outcome, we would essentially unlock the full spectrum of delta. By running the simulation for one final time and considering all the cumulative insights and precise decision tree, our subject would navigate towards her predefined objectives with high levels of precision. And this represents the very essence of the delta level. The exploration of our test subject doesn't stop at this delta level, because the true depth of our simulation lies in challenging the very foundation of our journey. So what if we want to aim outside of our predetermined starting point? Welcome to Epsilon. We are about to alter an initial condition that has so far dictated the course of our subject. So what is that focal point that could demonstrate the impact of a different starting point in this case? Well, how about changing the lab assistant at the start of the simulation? A completely new person can play a crucial role in shaping the research direction, dynamics of lab management, and the overall approach to academic challenges. We can see how different skill sets and personalities can lead to vastly different decision trees and outcomes. Let's visualize how this works in practice. The presence of the new lab assistant modifies the initial nodes of the decision tree. The QDMI device is then recalibrated to reflect these changes. We can see a new set of decision paths appearing from the outset. There will be scenarios that specifically highlight the deviation from this new tree. Like their expertise might open up different methodologies, or there could be conflicting ideas when you work together. Then we'll use the scenario reiteration feature to allow revisiting decision points with this new character. That way, we can explore alternate paths within this new initial condition. We can encourage the test subject to experiment with different approaches to see how this assistant alters outcomes. After we map out all the possible decision trees and their consequences, we will have a hierarchy similar to the ones we mapped in Delta. It's just that now it's a parallel version where we start the model from a different starting point. Now let's take this further. What if we can map out all the different initial conditions, or in this case, the different choices of lab assistants? where we would run all the parallel hierarchies and have a complete overview of all possible planes of different starting points. And that's the next level of this quantum simulation, aka the lambda level. Okay, the distinct nature from epsilon to lambda is the idea that you'll have knowledge of the planes of different starting points to choose from. It's like having an overview of the whole maze without even having to run each simulation to know the path to your objective. And so, while epsilon has the ability to navigate different decision trees, lambda has the full plane of all decision trees already mapped. But the question becomes, how do we achieve that in our simulation today? Well, you guessed it. To build these planes, we have to conduct parallel simulation runs. So first, we introduce an infinite array of characters for the lab assistants, each with their own skills, levels of expertise, and other values as our toggles here. Then, we run multiple simulations in parallel, each starting with a different lab assistant. Don't worry, let's assume that we have enormous computing capability for this quantum simulation. We would then observe how each choice influences the decision tree, the research outcome, and the overall trajectory of our test subject. Perhaps in some simulations, we'd find that a specific assistant could handle complex tasks autonomously, which would then free our subject so she could focus on other strategic areas. As we run through these parallel simulations, we also have to consider variations in objectives for each run. Things like the longest career span, the most dramatic research breakthrough, or perhaps the fastest completion of the main goal. We can analyze how different arrays of initial conditions influence the likelihood of achieving these objectives. By the end of this, we'll have developed a comprehensive understanding, an enormous database full of decision trees, and how each one of them can be strategically leveraged to achieve specific goals for our subject. But let's ponder a deeper question at this point. Sure, we've navigated through a labyrinth of decisions and parallel narratives. We can also identify the most advantageous routes for our subject to reach her goals. But what next? What if there's more to this vast database? What if we could decipher the very fabric of her reality, the fundamental parameters that construct her world? So welcome to this Sigma level. Okay, so our objective here is to uncover the secret engine of Dr. Allen's universe, meaning the intricate lines of code and algorithms at the core of the simulation. The way we do that is to focus on predictive analysis. It's kind of like a detective piecing together a complex puzzle. And so let's revisit this database again. This enormous array that we collected from the lambda level will be analyzed for a lot of different variables. Things like consistent outcomes, recurring numerical values, and specific sequences of events. We can use Grover's algorithm to quickly locate specific decision paths that are of interest for our hypothesized engine modeling. Some of this hypothesis could include probabilistic decisions. We need to analyze how choices lead to different probabilities of an event. Like in this case, we make a guess that the success rate is a 70% chance by collaborating with scientist number 182. Number 2, trigger events. There should be specific conditions that trigger certain events in our subject's world. Like discovering that publishing in a top-tier journal triggers invitations to elite conferences. Character interaction. We analyze how interactions between other characters affect outcomes. After all these, and perhaps gigantic numbers of other variables, we formulate hypotheses of the predicted model in each of those lines, corresponding to the complete dynamics of her simulated world. We can refer this process as engine rule extraction. When we run simulations based on this hypothesis, we need to observe if the outcome can be accurately predicted using our rule. For instance, simulate the scenario where our subject collaborates with different scientists. We can then observe if the success rate aligns with the hypothesized 70%. If not, adjust our rule based on this new info, and then rerun. Once we decipher these secret laws of physics, the sigma level allows for an unprecedented manipulation in our subject's reality. So to demonstrate this, we start by replicating the complex lines of code that form the foundation of Dr. Allen's world. But rather than making changes directly to this primary world, we take a subtler approach. We create a mirrored version of her reality, a kind of parallel space that exists within the original simulation. This is a special domain where our subject can safely experiment with the fabric of this newly formed reality. Within the secondary world, she has the power to alter the constants and rules that govern this inner universe. This methodical approach allows her to see how each modification in the mechanics of her simulation can shift the trajectory in this microcosmic realm. Now, you can create a line of code that literally smooths your trajectory to your goal, even when you've chosen the least competent lab assistant. By altering the fundamental rules and parameters of the simulation, we can create scenarios that deviate drastically from standard gameplay expectations. In the end, this whole approach is to demystify the complex laws of physics that govern the world of our subject. And that's the world of Sigma. We finally arrived at the final frontier, Omega. This realm is where we map out all conceivable arrays of the laws of physics within her subsimulation, essentially creating a universe of boundless possibilities. Let's search for something peculiar in this database that we've already mapped out here. Here it is. Back at the sigma level, we altered this parameter so that when the grant proposal number reaches 74, instead of ordinary events, she receives 13 balloons. I mean, that's quite unusual within the standard framework, isn't it? What about discovering another unusual phenomenon within this array? We've previously transformed it from attending a conference to gaining mind-reading abilities or teleporting to another world. And so in Omega, we can not only experience but also map out all these diverse pathways, becoming the architects of each reality. This level goes beyond merely playing the game. It's about mapping every conceivable scenario and rewriting it. We possess the ability to reshape Dr. Allen's world in ways that challenge the very concept of her reality. As we delve into this ultimate level of simulation, an intriguing thought emerges from the depths of our creation. That every rule we've altered, every scenarios that we've crafted, it's always been us at the controls. We've been the puppeteers of Dr. Allen's world and the intricate layer of her sub-simulation. What if we step back and look upward? Could it be that our own reality, the world we perceive as tangible and absolute, is itself a construct of a higher order? The simulation hypothesis by Nick Bostrom becomes really pertinent. Bostrom suggests that if future civilizations reach a point where they can create numerous simulations of their ancestors, it becomes challenging to be sure we're not in one of those simulations right now.
That there is some advanced civilization who built a lot of computers, and that what we experience is an effect of what's going on inside one of those computers, so that the world around us, our own brains, everything we see and perceive and think and feel would exist because this computer running certain programs.
In a simulation, experiences feel just as real as in the actual physical world. So, based on the principle of indifference, the chance of us being in a simulation is equal to the number of simulated beings that exist. And so, if we, with our current quantum technology, can construct worlds so complex and believable for Dr. Allen, isn't it plausible that our own reality might be a sophisticated simulation operated by a more advanced being? Perhaps, in the grand scheme of this vast universe, we are not the puppeteers we perceive ourselves to be. We might just be intricately woven puppets in a grander simulation, unknowingly dancing to the tunes of a higher reality.